All right, welcome. In this video, we're going to be reviewing Algebra 2, Unit 9. And I'm going to be working through the review, which actually says extra review problems. It's because I had put a bunch of stuff out to review before the break. And I'm going to do this. And then after I've done all of these problems, I'm going to come in and I'm going to do the extra practice on applied context and recursive formulas. And that'll just be at the end of the video. Or the second half. I don't know how long it's going to take. I'm going to need some scratch paper. As you will also, so we're not gonna try to cram our answers in over here. That's not gonna be the thing to do. So the first one, the graph of y equals a times b to the x is shown above. What is the value of a? Well, I can find that by looking at the place where x is equal to 0, right? Because if x equals 0, y equals a times b to the 0. B to the 0 is going to be 1. So that's equal to a. So I look over here where x is 0. I see y is 4. And so I'm going to say a is equal to 4. Okay. For 1b, is b positive or negative? Okay, it's going to be positive. We don't deal with negative bases of exponentials. Okay, that was, I'm not... Well, maybe I was trying to, when I made these problems, I was trying to remind you of that we're really only dealing with exponentials that have positive base. If you think about it, negative 1 to the x is going to be a really weird function. Okay. If x is allowed to be any real number. If it's just integers, just bounces back and forth from negative 1 to 1. Is the absolute value of b greater than 1 or less than 1? This is something that we definitely should know. Okay, so 1c is going to be, okay, I'm seeing exponential decay. So that means that each time x bumps up by 1, I'm multiplying by something. But it's getting smaller, getting closer to 0. So I got to be multiplying by basically what you would call a fraction. And so I'm going to say absolute value of b is less than 1. Okay. And like I said absolute value just to make sure that worked. I don't know, whatever. Number 2, let's sketch some graphs. So I'm going to start with e to the negative x. That's just kind of standard exponential decay. Yeah, just 6 of these. All right. Exponential decay, kind of like the graph up at the top. It's going to kind of come from above, and oh man, that was bad. But it'll do. Okay, for the kind of sketches I need you to make, I need you to know the shape of the graph, the fact that it lives above the x-axis, it intercepts it, y equals 1. That would be nice. Also just the shape. B. Okay, I'm going to draw, okay, negative of e to the x. Okay, it's like exponential growth, but upside down. Okay, so I'm going to say, okay, I'm going to need like more room in the negative y territory. And see, the bigger x gets, the more negative e to the x would get, right? Because we have exponents before multiplication by negative 1. I'm going to take e to that really large power, and then I'm going to make it a negative number, a huge negative number. So 2c is going to be y equals negative e to the negative x. Right, that one's going to be below the x-axis, right, because of the negative here, but because of the negative up here, it's going to be exponential decay. So it's negative, but getting closer to 0. D is 1/2 to the x. I feel like I may have neglected that a little bit in this, I don't know. It's hard to remember because it's been a while. But 1/2 to the x that's the same as 2 to the negative x, if you think about it, with exponent properties, 2 to the negative 1 being 1/2. So this is just going to be pretty standard. Exponential decay, just like e to the negative x. I was intended for those to look pretty much identical. 2e is going to be negative of 1/2 to the x. Okay, so it's going to be this thing, right? It's the exact same function, just multiplied by negative 1. So all of the y coordinates will be multiplied by negative 1. Okay. So, but as I move left to right, I'm getting closer to 0, so that's going to be like that. Okay, and then 2f is 1/2 to the negative x. Okay, that's a little tricky. I'm going to do some algebra off to the side. Maybe a different color pen. Just red. So 1/2 to the negative x. This is kind of like what I was talking about earlier. All right, this is 1/2 to the negative 1 to the x. And 1/2 to the negative 1 was just 2 over 1. This is just 2 to the x. Okay, so this is just standard exponential growth. Okay, and that might be a little beyond the scope of what I would ask you on a quiz or a test, but, you know, good problem for reviewing. All right, that was number 2. Number 3, this was a thing that y'all kind of struggled on when we did this in the lessons and on the quiz and stuff. So I made sure to put more of this stuff on the review because it's going to be on the test for sure, right? You know me. Especially if y'all struggle with something, I'm going to give you an opportunity to redeem yourself. And so I've got all this stuff. You know, another thing, I was talking to people in class about this one today. I'm going to recommend, okay, we've got A, we've got B, we've got C. We might also write out what is the log with base 5 of 5, right? That's going to be equal to 1 because the log base 5 of 5 is the exponent I put on 5 to get 5. That's 1. So I've got these 4 pieces of information, and that will be enough for me to solve these. All right. So A, log base 5 of 28. And the idea with these is that we make up the argument number, 28, 1.75, 49, out of 4, 7, 9, and potentially 5. Okay. So I'm going to say, what's 28? That's 4 times 7. Okay, so A, I'm going to say log base 5 of 4 times 7 is equal to log base 5 of 4 plus log base 5 of 7. And that's going to equal A plus B. Right, I'm definitely not going to be able to fit all of these. I'll figure out a way. B is log base 5 of 0.25. 0.25 is 1/4. Okay, so I'm going to make that out of the 4. I'm going to say that's 4 to the negative first power. Okay, and if I've got an exponent on the inside of the log, I can swing that around the front with multiplication. So that's negative 1 times the log with base 5 of 4, and that's just going to be negative A. Can't see that, but that's what I said. All right. Let's see. Oh, maybe I'll zoom this out a little bit. Yeah, that will be helpful. Okay, let's just keep that going up for a little bit. All right, I think that will allow me to fit all my work in here. Log base 5 of 1.75. 1.75 is 1 3/4, so that would be 7 divided by 4. Okay. I've got division on the inside of my log. I'm going to rewrite that as a difference of 2 logs. Log base 5 of 7 minus log base 5 of 4. And log base 5 of 7 is B. Log base 5 of 4 is A. This will be B minus A. Right. D is log base 5 of 45. 45 is just 9 times 5. Okay, so that's going to be log base 5 of 9 plus log base 9 of 5. Wait, no. Base 5 of 5. I didn't have that other thing. But I've got all this here. Log base 5 of 9 is C. Log base 5 of 5 is 1. So it's going to be C plus 1. All right, for E, I'm going to have log base 5 of 49, which is 7 to the 2, or 7 times 7. Doesn't matter. You're going to end up with 2 B's anyway. And so I'm going to say, you know, maybe you could write it like that and write it as addition, and it would be B plus B, or you could say it was 7 to the 2, and that's 2 times the log base 5. So that's 2B. Right, with F, I'm going to have log base 5 of 49 over 4. So what I'm going to do is, well, I could say it's this times 7, but I'm not going to do that. I'm going to cook up 49 over 4 by writing that as 7 squared divided by 4. Because I've got info about x equals 7, or log base 5 of 7. I got info about log base 5 of 4. I should be able to make this happen from here. All right, so first I'm going to deal with the subtraction, I think. Okay. And on this one, okay, I can swing that around the front. 2 times the log base 5 of 7 was b, minus the log base 5 of 4, that's a. 2b minus a. All right. G. This was the one that I ended up doing a bunch of times in class in all of my sections. So I'm going to say that was, I'll just put that here. Okay, log base 5 of 81 over 20. Now this, I will admit, is a bit beyond what I would ask you to do on the test. But it's still good algebra. So log base 5 of 81 is 9 squared minus, okay, because I'm splitting it up over this division here. Now, this multiplication is going to get split into an addition of 2 logs, right? And I'll switch up the color here. So it'll be log base 5 of 4 plus log base 5 of 5. And we have information about both of these, but I'm subtracting this whole thing. So that means I need to subtract both of these 2. Okay? So both of these are going to be negative. That's what I'm saying. Well, and that'll be 2 log base 5 of 9. Okay, so I've got 2c here, minus, and then log base 5 of 4, that was a. Log base 5 of 5, that's 1. And, okay, so you could, I think you could stop there, that'd be fine. If you wanted to go a little farther, that would be 2c minus a minus 1. And the a and the 1 are both negative because the a and the 1 come from the 4 and the 5, right? And they're both in the denominator of the original log, and that's why they're both negative. H, I think it gets a little, yeah, it gets a lot easier after those. Log base 4 of 7. It's like, wait a second. Was this a typo? It was not, right? We only have logs with base 5. But 4 and 7, I have both of these. So what we're going to do is we're going to use the change base formula. We're going to change to log base 5 of 7 divided by log base 5 of 4. And that will be b divided by a. That's a little different. That's also probably one that's a little beyond what I'm going to ask you on the test, but just thought it would be good practice. I log base 5 of 2. Okay, how am I going to write 2 in terms of 4, 7, and 9? 4 is the square root of 2. And so I'm going to use that exponent property, swing it around the front. 1/2 log base 5 of 2. No, hold on. I said 2 to the 1/2. I meant 2 is 4 to the 1/2. And if the log base 5 of 4 is a, this will just be half of a. Or a divided by 2, however you like. Okay, that's I. What about j? Oh, this one's ended with some good ones. Log base 5 of the cube root of 9. Well, I'm going to write that as 9 to the 1/3 power, so I can utilize that exponent property. 1/3 of the log with base 5 of 9. Log base 5 of 9 is c, so that's going to be 1/3 of c, or c divided by 3. And that's all for number 3. Had a lot going on. But that's good practice. That's what we need. All right. Zoom back in here. All right, yeah. Number 4. We're going to let f of x equal the log with base 9 of x minus 2. And I think I can actually reverse this so that that is sitting right down there at the bottom. Yeah, perfect. Okay, that'll be good. So if we're going to find the domain and range of f, okay, the domain of a log function, the thing that we input has to be positive. Okay, so x minus 2, the argument of the log has to be positive. So I'm going to say right here, 4a is going to be domain x minus 2 greater than 0, meaning x is greater than 2. And the range of any of these log functions is going to be all real numbers. For 4b, find the value of f at the given x values. Okay, we'll do that. F of 3 is going to equal the log base 9 of 3 minus 2. So log base 9 of 1. 9 to what power equals 1? 9 to the 0 power equals 1. Okay, great. F of 19 over 9. Okay, so if I take 19 over 9 and I subtract 2, 2 is 18 over 9. So if I plug in 19/9, I'm taking the log with base 9 of 1 over 9. What exponent do I put on 9 to get 1/9? That'll be the -1 exponent. F of 5 is going to equal log base 9 of 3. What exponent do I put on 9 to get 3? 3 is the square root of 9, so I'm going to put the half exponent on there. X equals 83. Okay, if I subtract 2 right here, I'm going to get 81 on the inside of the log. Okay, that looks like something I could probably take. Okay, what exponent do I put on 9 to get 81? I put this 2 exponent on there. X equals 17 over 9. Ah, yeah, I like that. Okay, if I subtract 2 from 17 over 9, 2 is 18 over 9. So I'd be taking the log with base 9 of -1/9. And that doesn't exist because there's no exponent I can put on 9 to get -1/9. There's no exponent I can put on 9 to get anything that's negative. But also, 17/9 is less than 2, and we said the domain of this function is where x is greater than 2. So x equals 2, that's probably going to be bad news as well. F of 2 is log base 9 of 0, which also does not exist because there's no exponent I can put on 9 to get 0. Okay. We're going to just solve some equations. Right? Hopefully this goes well. Okay, for C. F of x equals 3/2. So log base 9 of x minus 2 equals 3/2. I feel like we solved, this is a quiz question because I just recorded that and I feel like I just solved this equation. Anyway, I'm going to take 9 to both sides power. So 9 to the log base 9 of this is just going to be this. And 9 to the 3/2 is the square root of 9 is 27. No. I got ahead of myself. Square root of 9 is 3. 3 to the third is 27. So I ought to write that out. Yeah. Okay, and so then I'm going to solve for x by adding 2 to both sides, and I'll get 29. All right, there's only 4 of these, so f of x equals 1. That'll be log base 9 of x minus 2 equals 1. I'm going to take 9 to both sides power, so I'll have, that's just x minus 2 is 9 to the first. So that means x equals 11. I think I could probably fit one more in. No, just scoot it over here, squeeze them in there. All right, f of x equals -1/2. So log base 9 of x minus 2 equals -1/2. And this is fine for a log to equal a negative number. It's just we can't put a negative number on the inside. All right, so 9 to the -1/2, 9 to both sides power, gives me x minus 2 is 9 to the -1/2. Which is 1 over the square root of 9, and that's 1/3. So x minus 2 equals 1/3. 2 is 6 over 3. So I'm going to add that over here, and I'm going to get 7/3. So x equals 7/3. This last one, f of x equals 3. Okay. Log base 9 of x minus 2 equals 3. So we're going to take 9 to both sides. I'm going to get x minus 2 equals 9 to the 3. 81 times 9, 80 would be 720, 729. Okay, I do have that. If I add 2 to both sides, that would be x equals 731. And now, 9 to the third, that's definitely a number you could look up over on my table of values, the calculating poster. We've got not really. Oh, it's different. Not a whole lot on the backside. Okay, so that was number 4. Number 5. I'm going to do the same thing. Let's put the actual problem over there. All right, find the domain and range of g. Okay, the domain of an exponential function is going to be all real numbers because there's nothing illegal for me to put in for x, right? As long as x is a real number, we can take 5 to a real number power. Might be hard, but we can do it. So 5a will be right here. Oops. 5a, domain and range of g. Domain is all real numbers. Okay, the range is a little trickier. Okay, it all starts with the fact that 5 to the x is positive. Okay, for any x, 5 to the x is going to be greater than 0. And so if I multiply it by 3, that's still going to be greater than 0 because I'm multiplying both sides of the inequality by 3. Then reverse the direction. 0 times 3 is still 0. And then I'm going to add negative 9. That's going to be greater than negative 9. I'm just adding negative 9 to both sides. And I'm going to say that, well, that's a formula for y. Y is greater than negative 9. And if you can just determine that by looking at the equation, great. Go ahead, do that. But if you need to work through the steps, that's what you do right here. Right. For 5b, if k is log base 5 of 10, find g of k. All right, I can do that. I'm going to say, all right, g of k, I'm not going to write that all out, is equal to negative 9 plus 3 times 5 to the log base 5 of 10. Yes. All right. Now, remember, exponents before multiplication in PEMDAS. Exponent of this log before multiplication by 3. So 5 to the log base 5 of 10, that's just 10, right? And I'll remind you why that's true. I've only, lately just been saying, hey, it's a fundamental identity. You need to know it. But just to remind you why it's true. Remember that log right here is the particular exponent that you would put on 5 to get 10. Okay? And so we're putting that exponent on 5, and we're going to get 10. So negative 9 plus 3 times 10, 30 minus 9, that's 21. X and y intercepts of g. Oh, I'm realizing I did not sketch the graph on number 4. And I will do that when I go to sketch the graph on number 5. But the thing is, sketching the graph on number 4 is not going to be a big scheme of things because it's beyond the scope of what I'm going to ask you to sketch on the test. I'm going to ask you to sketch one like this, but not one with a log that's been like shifted around. Right? Do that a different day. So 5c is x-intercept. All right. Maybe I'll do the y-intercept first because that's a little easier. That's where x is equal to 0. So I'm going to say g of 0 is equal to negative 9 plus 3 times 5 to the 0. Well, 5 to the 0 is 1, so negative 9 plus 3, that's negative 6. And I think that'll help us when we go to make our sketch. Okay, then x-intercept, that's where y equals 0. So I'm going to take g of x and I'm going to set it equal to 0. Negative 9 plus 3 times 5 to the x equals 0. So I'm going to add 9, divide by 3, and then take a log with base 5 of both sides. And well, I don't know exactly the value of this log, but I know it's going to be less than 1. Okay, because the exponent I raised 5 to get 3, it's going to be less than 1 because 5 to the 1 is 5. And 5 to the x is an increasing function. All right, that was C. D, find the value of g at the given x values. Okay, I'm start to run into whatever I had printed over here. Looks like some differential equations. Yeah, but this will be easy enough to evaluate. So if I need more room, I'll just get a post-it note. All right. At x equals 1, I've got negative 9 plus 3 times 5 to the first. Okay, 3 times 5 is 15. 15 minus 9 is 6. G of 3 is negative 9 plus 3 times 5 to the third. 5 to the third is 125, so 3 of those would be 375. And if I subtract 9, will that give me 366? Okay, so we won't be needing x equals 3 on our sketch. X equals negative 2. G of negative 2 is going to equal negative 9 plus 3 times 5 to the negative 2. Okay, 5 to the 2 is 25, so 5 to the negative 2 is 1 over 25. All right. Well, I'm not sure if y'all are aware of this, and I think I'd be fine with this response. This is arithmetic that's a little bit beyond what we do in my class, but 1 over 25 is 4 cents, right? So I'm going to say that's 12 cents if I'm multiplying it by 3. Negative $9 plus 12 cents is going to be negative $8.88. And then the last one would be, where is it? Oh, sloppy, I did not change that. I'll change that one on that one that's posted on the internet for sure. Okay, the last one is x equals half. That's equal to negative 9 plus 3 times 5 to the 1/2. I guess that would be 3 root 5. Hey, that's going to be as far as I'm going to take that. Yeah, that'll be fine. And then we're going to sketch the graph of y equals g of x. Okay, I think I'm going to switch over to a different piece of paper to do this. All right, so 5D, and this is where I'm going to correct the mistake I made earlier, not graphing 4D. All right, so 5D. I'm going to say, all right, the function was g of x equals negative 9 plus 3 times 5 to the x. Okay, so this 5 to the x is exponential growth. It's 3 times as big. And then I'm going to subtract 9. So a normal exponential growth would have a horizontal asymptote of y equals 0, x-axis, whatever you want to call it. But since I've moved it down by 9, subtracting 9 from everything, the range of this was also y is greater than negative 9. So I'm going to say that this asymptote is y equals negative 9. Now the x-axis, that's going to be where y equals 0. Let's see, what was the x-intercept of this thing? Log base 5 of 3. So I don't know, that didn't mean anything to me. So I'll just draw that about here, and I'll be sure to mark that. Log base 5 of 3. But that is going to be bigger than 0. Okay. Also, we found that the y-intercept was negative 6. So if this is my x-axis, and I'm going to draw the y-axis, I can either draw it to the left of this or to the right of this, right? And I know that the y-intercept's negative, so I'm going to draw it right here. And that is just an excellent sketch of that function. Okay, that's probably more than I expect from you. I'm looking for the shape, the asymptote, and maybe the intercepts to, definitely the intercepts have the correct sign, positive or negative. Okay. But I think that's going to, I guess I could label this as negative 6. Figure is not drawn to scale. Okay, that's probably goes without saying when I'm just drawing freehand, but I want to make sure. All right, 4D. Forgot to do that one. I think that's back over here. Let's see where the problem set is. 4 was log base 9 of x minus 2. Okay. What's going to happen, I think what we saw was that the domain of this thing is x is greater than 2. We have, all right, so I'm going to say, all right, for a normal log function, the y-axis, x equals 0, generally serves as a vertical asymptote. This time it's going to be x equals 2 because that's the edge of my domain. And I know what the shape of a log graph looks like. Is it as that vertical asymptote and then it really levels off. Really, it's like a sideways exponential graph. Okay, so that's my x equals 2. X equals 0 is the y-axis, so I'm going to draw like that. And what was I thinking here? The base 9 of x minus 2. I don't know. That's my y-axis. Oh, what I was wondering was, did we not look for an x and y intercept of this thing? No, we didn't. Okay. Well, let's see, did we actually solve for it? We did. F of 3 equals 0. So that means that 3 will be my, x-intercept. We didn't do f of 0, But had we done f of 0, it would have been log base 9 of negative 2, and that doesn't exist. So that's fitting with what we're seeing. Also, domain is bigger than x bigger than 2. All right, that's going to be all for this graph. This is I mean, I guess I could label these axes, and then it would be a really nice graph. That's going to be all for this graph. So number 6 is going to be, wait, I didn't, man, this is, hope you can forgive me. I guess I'll just, I'll make the video chapters so that it's a little more clear what I'm doing. All right, so solve the equations. G equals 66. I'm going to just post-it notes for this, I think. All right, if G equals 66, that's going to be 66 equaling negative 9 plus 3 times 5 to the x. Okay, and I'm going to add 9 to both sides, and that'll be 75 equals 3 times 5 to the x. Okay, I see this is going to go well. Divide by 3. 75 divided by 3 is 25 equals 5 to the x. This is one we can solve with our eyes. X equals 2. We don't need to take sides. We could. It would still give us x equals 2, but I don't think it's necessary. Okay, G equals negative 8.4. Okay, negative 8.4 equals negative 9 plus 3 times 5 to the x. And I'm going to add 9 to both sides, and I'm going to get positive 0.6 equals 3 times 5 to the x. I'm going to divide both sides by 3, and if I have, say, 60 cents and I divided it by 3, I'd have 20 cents. That would be 0.2 equals 5 to the x. Now, this might be one you can solve with your eyes, but it might not be. Okay, what you would need to know is that 0.2 is 1/5. And how you would come to that if you didn't just immediately know it is that you would need to know that 0.2 is 2 over 10. 2 over 10 can be reduced to 1 over 5. So I'm going to say 1/5 equals 5 to the x. That's going to give, this is one we can solve with our eyes. Okay, what exponent do I put on 5 to get 1/5? X equals negative 1. Okay. Then I'll scoot it down 1, and I'll have g of x equals negative 18, and g of x equals 9. All right, so negative 9 plus 3 times 5 to the x equals negative 18. Okay, good. I'm going to add add 9 to both sides, and I'll get 3 times 5 to the x equals negative 9. 3 is a positive number. 5 to the x is a positive number. You can't multiply two positive numbers and get a negative number. I'm going to say right now, no solution. And then g of x equals negative 9. Oh, this one's also going to have no solution. So negative 9 plus 3 times 5 to the x equals negative 9. Okay, that's basically saying 3 times 5 to the x is equal to 0. Same story here. 3 is a positive number. 5 to the x is positive. Positive times positive. It cannot equal 0, so this has no solution. Okay. Now we're done with number 5. Okay, so number 6, we're just going to solve some log equations, and I think I'm going to just try to cover this up. Yeah. 4 times log base 2 of x minus 5 equals 20. And we're going to give exact values for this. So I need to isolate the log, divide both sides by 4. Okay. Now I'm going to need to take 2 to both sides power to get rid of the log. So 2 to that log 2 equals 2 to the 5. 2 to the 5 is 32. 2 to the log 2, that's going to be x minus 5. And that's going to give me x equals 37. Add 5 to both sides. Right, I'm going to move on. B is log base 3 of, give exact values. They're going to be, okay, I was going to say, like, starts with a log. It should probably be a whole number or something. For B, I'm going to have to combine these together with log property. Okay, so I'm going to combine them into a single log by multiplying their arguments. So x minus 80 multiplied by x, I'd have to multiply both of these things by x. It'd be x squared minus 80x. And that's going to equal 4. Then I'm going to take 3 to both sides power. Okay, 3 to the 4 is 81, equaling x squared minus 80x. Okay, quadratic, I got to set this thing equal to 0. Get the original problem out of the way. X squared minus 80x minus 81 equals 0. Two numbers that multiply to 81 while adding to negative 80. Wait, multiply to negative 81, add to negative 80, that would be negative 81 and positive 1. So I've got x minus 81 times x plus 1 equaling 0. Okay, that would give me x is either equal to 81 or x is equal to negative 1. Negative 1 is going to be an extraneous solution, not just because it's negative, but because it causes me to take the log of a negative number. It actually causes me to do it twice. Okay, so that's going to be an extraneous solution. We're just going to have x equals 81 only. Now we're going to work this next one. 5 minus 2 natural log of x equals 6. So I'm going to isolate the natural log, subtract 5 from both sides. Yeah, okay, that's going to be fine. That's negative 2 natural log x equals 6 minus 5 is 1. Isolate the log by dividing by negative 2. 1 divided by negative 2, that's negative half. And then I need to take e to both sides power to get rid of a natural log. All right, so x equals e to the negative 1/2, or we could write that as 1 over the square root of e. And for d, 2 to the x plus 3 plus 4 equals 10. Okay, so that means that the 2 to the x plus 3, that's going to need to be 6. That's something that we can kind of tell. And that's what we would find if we subtracted 4 from both sides of the equation anyway. So 2 to the x plus 3, when I subtract 4 from both sides, will equal 6. And then I'm going to take a log with base 2 of both sides. So I'll have x plus 3 equals log base 2 of 6. But there's nothing I can do with that. Yeah, there's no exponent I can put on 2 to get exactly 6 that I know of, right? It's going to be some bad number. So going for an exact solution, we're just going to leave it like that. And then I'm going to subtract 3 from both sides. Now, you can say log base 2 of 6 minus 3. If you do that, I'm going to really encourage you to put parentheses around the 6. To avoid that situation, I'm going to subtract 3 from both sides, and this will just be negative 3 plus the log base 2 of 6. Then we don't have to worry about parentheses or worry about being unclear or anything like that. There's only one thing that's going to be. Okay, that was d. One more. 4e to the x plus 1 equals 0. Plus 1 equals 0. Okay, let's see where this is headed. 4e to the x plus 1 equals 0. I'm going to subtract 1 from both sides. Divide by 4. Okay, and maybe you see it, okay, e is a positive number. Any power of any positive number is going to be positive, and this is not. So this is going to have no solution. If you didn't, you would take x equals natural log of negative 1/4, and that doesn't exist because negative 1/4 is not an argument that we can put inside natural log. Okay, so this does not exist, no solution, no some sort of indication that that went bad. That'll do for me. All right, now the next thing is solve the equations and use the log table down here to approximate the solution. Let's zoom out by one level. I think I'm just going to copy these problems. All right, 7a is 5 plus 2 to the x equals 14. Okay, so I'm going to subtract 5 from both sides. Take a log with base 2 of both sides. Oops. And then, okay, that's an exact solution. An approximate solution, I would have to use the change of base formula, which would be natural log 9 divided by natural log 2. Now, this itself is an exact solution. But when I go and I look up natural log of 9 from the table, I get 2.2 divided by natural log of 2, which is 0.7. So that's 2.2 over 0.7. That's 22 over 7. Wait, isn't that? It's approximately pi. Very close numbers. But not exact. The 3 to the 3e to the x minus 3 minus 4 equals 8. So I'm going to add 4 to both sides, divide by 4. No, divide by 3. Then I'm going to take the natural log of both sides. Okay, so that'll get the variable down out of the exponent, or the thing down out of the exponent. Okay, and then I'll solve for x, and that's 3 plus the natural log of 4. Okay, that's an exact solution. An approximate solution is going to be, okay, you look up natural log 4 from the table. That's going to be 1.4. You can't see that right there. 1.4 plus 3 is going to be 4.4. Whoops. Okay, and that's going to be just fine. See? 2e to the negative 3x equals 4. Okay. Isolate the exponential, divide by 2. Take the natural log of both sides. Guess divide by negative 3. Okay, it's going to be my exact value. And we can get an approximate, by saying, okay, natural log of 2 is 0.7. So I'm going to say x equals 0.7 divided by negative 3. That's also the same, 30 doesn't, or 7 doesn't divide 30, so that's going to be negative 7 over 30. If you had to write it as a simplified fraction, I don't think you do. Okay, and then the last one, 7d, would be 2 times 10 to the x plus 1 equals 11. Okay, so I subtract 1, divide by 2, take the common log of both sides, so the log base 10 of 10 to the x, and that's just going to be x, is log base 10 of 5. So x equals log base 10 of 5. That's my exact value. In order to get an approximate value, I'm going to use the change of base formula. That'll be natural log of 5 divided by natural log 10. Look those up from the table. Wait, I feel like I did something wrong here. Okay, who knows? 1.6 divided by, that was natural log 5. Natural log 10 was 2.3 on the table. And at 16 over 23, that'll be fine. Not sure what it would be if I was forgetting something, but all right. The last problems is, say, use the table of logs to approximate the values. I do think I'm going to leave that one on screen. Oh, it's just not quite. There we go. That'll be fine. All right. Natural log of 6e. Okay, that's a multiplication on the inside. I'm going to write that as natural log 6 plus natural log e. Okay, natural log 6, we looked that up from the table, that's 1.8. Natural log e is the exponent I put on e to get e. Or maybe you think of it as e to the 1. Use fundamental identity. Either way, it's going to be 1. That'll be 2.8. 8b, natural log of 100. That's not on my table. Okay, so what am I going to do? Write it in terms of the numbers I do have on my table. So this is more log property practice, really. It's going to be 10 times 10. Whoa. Natural log of 10 times 10. Okay, so that'll equal natural log 10 plus natural log 10, which will be 2.3 plus 2.3. That's going to be 4.6. Or you could have said that's 10 squared, and 2 times 2.3 is 4.6. Either way, you're going to get 4.6 if you do it right. Okay. Was A and B, a little hasty. 8c is going to be natural log 88. How can I make 88 out of the numbers I've got in this table? 8 times 11. I'm sure there's other ways, but it would be more complicated. So I'm going to say natural log of 8 plus natural log of 11. 2.1 plus 2.4. And that's going to be 4.5. Okay. And that does make sense. right? That the exponent you would put on e to get 88 would be less than the exponent you would put on e to get 100. Now the fact that it's only off by 0.1, well, that just goes to show you how fast growing the function e to the x is. 8d is natural log of e to the 5. Okay, I'm glad I put one of these on there. That is 5. Okay, natural log of e to any number is just that number, right? Because the natural log is the exponent you put on e to get e to the 5. Let me say that again. It's the exponent you put on e to get e to the 5. That's the 5 exponent. Okay, not a trick question here. So 8e, natural log of 2 over the square root of e. I might rewrite that over the square root of negative e. I might just call that 2 times e to the negative 1/2 power, right? Half because it's the square root, negative because it's in the denominator. So I'm going to go over here, and I'm going to say that this is equal to natural log of 2 plus natural log of e to the negative 1/2. I really like this. It used our fundamental identity, and that's why I kind of always default to. Natural log of 2 is 0.7 plus, hey, that's just negative 1/2, which is negative 0.5, and that'll be 0.2. That's cool. All right, that's going to be all the problems for the review proper. I am not going to have time to record solutions for the applied context and recursive formula thing right now. I'll record that sometime later today or tomorrow or something. And so I guess you're going to have to just see that in the next video. But I bet that I can make it suggest that video for you right now on screen. So that's going to be all that I've got for you for this video. Thanks for watching. Really hope this helped.